This video is brought to you by mywayteaching.com.
In this part, let us see one more simple problem, that is example 8. Okay, a 5 kg collar is attached to a spring of spring constant 500 Newton per meter. It slides without friction over a horizontal rod. The collar is displaced from its equilibrium position by 10 centimeter and released. So here we should calculate the period of oscillation, the maximum speed and maximum acceleration of the collar. Okay. So these are the three things that we should find out with the given data in the question. So now coming to the solution part. So the first part of the question, so we should find out the period of oscillation, isn't it? Yes. And the period of oscillation is given by T is equal to 2 pi square root of m by k. And here they have given the value of m as 5 kg, and even they have given the value of spring constant, that is 500 Newton per meter. So substituting the values, we get 5 kg by 500 Newton per meter. We get 2 pi by 10 seconds, that is equal to 0.63 seconds. Okay. Coming to the second part of the question, here we have to find the maximum speed, isn't it? Yes. See, the velocity of the collar executing simple harmonic motion is given by minus AW sine omega t plus pi, and the maximum speed will denote it with Vm, that is equal to AW. Okay. So that is 0.1 into square root of k by m. Again, that is equal to 1 meter per second. So this is the solution for the second part of the question. Okay. Coming to the third part of the question, that is maximum acceleration of the collar. So it is given by A of t is equal to minus w square into x of t, which is equal to minus k by m x of t, because w is square root of k by m, and the maximum acceleration is given by A max, that is equal to w square into A, that is w is k by m, that is 500 by 5, and A is 0.1, which gives 10 meter per second square. Okay, and it occurs at the extremities. Now let us study about the simple pendulum. Okay, it is said that Galileo measured the periods of a swinging chandelier in a church by his pulse beats, and even he observed that the motion of that chandelier was periodic, which was it was repeating after regular intervals of time, and the system is a kind of pendulum. And even you can also make your own pendulum by tying a piece of stone to a long unstretchable thread, isn't it? You just take a long unstretchable thread and tie a stone to that, approximately 100 centimeter long. Okay, this thread should be approximately 100 centimeter long, and suspend your pendulum from a suitable support. You should also take some suitable support to suspend your pendulum so that it is free to oscillate. Okay. Displace the stone to one side by a small distance. Okay, you just displace this stone to one side by a small distance and let it go. Then that stone executes a to and fro motion. It is periodic with a period of about 2 seconds. You can see that kind of pendulum here. This periodic motion is a simple harmonic for some displacements from the mean position. Okay, you just consider a simple pendulum as you can see here. A small bob of mass m. Here you can see a small bob of mass m tied to an inextensible mass less string of length L. The other end of the string is fixed to a support in the ceiling, and this bob it oscillates in a plane about the vertical line through the support, and this figure it shows this kind of system. And this one figure it is a kind of free body diagram of simple pendulum showing the forces acting on the bob. You can see there is a tension, the force Fg, the normal force Fg is also acting, and that is resolved into Fg cos theta and Fg sin theta. Okay. See, the forces acting on the bob are force due to gravity Fg and the tension in the string, isn't it? Yes. Let theta be the angle between, okay, made by the string with the vertical. You can see here, this is the angle made by the string with the vertical when the bob is at mean position. Okay. there are only two forces acting on the bob, the tension T along the string and the vertical force due to gravity. And the force mg can be resolved into two components. One is mg cos theta and the another one is mg sin theta, which is perpendicular to it, isn't it? Yes, as here fg cos theta and fg sin theta. And since the motion of the bob is along a circle of length L and center at the support point, the bob has a radial acceleration that is given by W square into L, and also a tangential acceleration. This tangential acceleration, it arises since motion along the arc of the circle is not uniform. And the radial acceleration, it is provided by the net radial force that is given by T minus mg cos theta. This is the force which provides radial acceleration, while the tangential acceleration is provided by mg sin theta. Okay, this provides tangential acceleration. And even it is more convenient to work with the torque about support, since the radial force gives zero torque and the torque tau about the support is entirely provided by the tangential component, that is mg sin theta. This provides torque. The torque due to radial force is always zero. Okay. So we can write torque is equal to minus L mg sin theta. And this is the restoring torque that tends to reduce angular displacement, hence the negative sign. And by Newton's law of rotation, we know torque is equal to I alpha, where I is the what? Moment of inertia and alpha is the angular acceleration, isn't it? Yes. So this I alpha is equal to minus mg sin theta into L, or we can write in other words, alpha is equal to minus mgl by I sin theta, isn't it? And even we can simplify this equation if we assume that the displacement theta is very small. We know that sin theta is equal to theta minus theta q by 3 factorial plus theta phi by phi, and its equation continuous, where theta is in radians. So if theta is very small, we can replace this sin theta with only theta, isn't it? So we'll get the equation as mg L by I theta if theta is very small. See this table, it we have it gives the angle theta in degrees and even its equivalent values in radians and the value of function sin theta. For in 0 degree it is 0 radian, for 5 degree 0.087, And what is the value in sine theta? That is also given. Up to 20 degree it is given. And from this table it can be seen that theta as large as 20 degree, sine theta is nearly the same as theta is expressed in radians. Okay, it is almost same. To these two values are almost same, isn't it? See, for small theta, the motion of the bob is simple harmonic. So the value of angular frequency is given by mgl by I, and we can write the period t is equal to 2 pi square root of I by mgl, isn't it? Now, since the string of the simple pendulum is massless, the moment of inertia I, we can write it as m into L square. Then this equation gives the well-known formula for time period of a simple pendulum. That is I is equal to t is equal to 2 pi square root of L by G. This is the well-known equation for the time period of simple pendulum. Okay, we use in solving the problems in calculating the time period.